Here we have a volume of oxygen gas that is being collected over water at a temperature and pressure. We need to determine what the volume would be if we did the exact same thing at STP when it is dry. And what that dry means is that we're not collecting it over water. There is a very particular stipulation you must remember if you're going to collect gas over water. And that is, if you're given this pressure here, this 758, this total pressure is not the pressure of the gas. This is simply the pressure of the gas plus the water vapor pressure at that temperature. So that 758 is not necessarily the pressure of oxygen. It's simply the total when you factor in the vapor pressure. And if you notice, they gave us the vapor pressure of water at that temperature. So I could find the pressure of that gas, which is P total, minus my vapor pressure. So I'm going to get a value of 758 torr minus 17.54 torr. So the pressure of oxygen being collected is actually 740.46 torr. That's nice. So we know what the total pressure would be if we did the exact same collection, but dry instead of over water. Now it's asking us to find the volume of the same sample if it occupies at STP. So if I recall ideal gas law, which is PV equals nRT, we can take a look at what is going to change versus what's not going to change. And we don't have to do ideal gas law twice, because if things are remaining the same, I could just look at ratio values. So if I have a volume of oxygen gas being collected at a temperature and pressure, it's asking what is the new volume if I have STP, which is standard temperature and pressure. I'm changing the pressure and temperature and the volume. The only things that are constant are my N value and my R value, which means I want to get all of my changing variables on one side, all my constants on the other. So I can say that for every original PV over T, I will have a new series of pressure and volume over temperature. Because no matter what, N times R will be the same, because it did state it's the same sample of oxygen. So I don't have to do the ideal gas law twice. As long as I remember, I can set these ratios up. So we're looking for this new volume, volume 2. Okay, so our volume 1 is our original, volume 2 is our new. So I'm going to set up a series of ratios to solve for it. I'm basically going to multiply both sides by the second temperature and divide both sides by my original pressure, my second pressure. So V2 is simply V1 times my pressure ratio, which is pressure 1 over pressure 2, times my temperature ratio, which is temperature 2 over temperature 1. So like I said, all I did was I divided both sides by pressure 2, multiplied both sides by temperature 2, which is great. Now, as an aside, I just want to mention one thing about units. The pressure and volume units, sorry, that's not units, those are rates. The pressure and volume units, or in this case unit ratios, will be the same, but the temperature unit ratios will not. And the reason being is that it's based on the type of conversions that occur. So if I had a volume and I'm converting from one volume to another volume, those are all multiplicative. For pressure, those are all multiplicative as well. So if you were to take some value, divide that by 760, and divide both of those by a new pressure divided by 760, the 760s count. So what I'm really trying to tell you is the pressure in atmospheres over a new pressure in atmospheres is identical to a pressure in torr divided by the second pressure in torr. That ratio is the same. And the same thing for a ratio of volumes with liters or milliliters or cubic centimeters. But a temperature in degrees Celsius over a second temperature in degrees Celsius is not the same as the temperature in Kelvin over the second temperature in Kelvin, because the temperature conversion is additive. You need to do adding or subtracting to convert from one to another, and those ratios are not the same. So what I'm basically trying to tell you is I don't have to do unit conversions for pressure or volume, but I do always need to do unit conversions on temperature. Gas laws always require temperatures in Kelvin, especially with STP being a temperature is 0. You can't really use 0 degrees Celsius in a ratio, especially if it's on the bottom, because then bad things would happen if 0 is in the bottom of a fraction. So temperatures must always be in Kelvin. Pressures and volumes in terms of ratio values, you don't need to convert, but if you'd like to, you will always see this repetitive ratios are going to be the same. So my second volume will equal my first volume of 150 milliliters times my ratio of the new pressure, the first pressure, which I found to be 740.46 torr, divided by my my second pressure, which is STP. STP is 0 degrees Celsius in 1 atmosphere. But 1 atmosphere is the same as 760 torr. And 0 degrees Celsius is 273.15 Kelvin. Those are our unit conversions, if you recall. So I'm just going to divide my 740 by 760 torr. And now for my temperatures. I'm using my new temperature in the numerator, which is 0 degrees Celsius. I'm going to add that to 273.15. And then divide that by my original temperature of 20 degrees Celsius, which I'll add by 273.15. So this ratio of pressures, that value, is 0.974289. That ratio of temperatures is going to be 0.931776, not 0. The 0 degrees Celsius over 20 degrees Celsius, that's not a ratio of 0. Again, gas laws, Kelvin, always. So we multiply those two ratio values by 150 milliliters to get our new volume, which is 136.1729 milliliters. So our new volume, collected over dry conditions, is 136 milliliters. So the key to this is recognizing if you see the words collected over water, you must factor in the vapor pressure of water at that temperature, and you don't always have to do ideal gas law multiple times. As long as you know what units are going to be changing and what units are not going to change, you can set it up into a nicer ratio, and once you get these ratio values, you don't have to go through all these heavy unit conversions if you don't need to. However, always convert temperatures to Kelvin. Always, 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 always.